Hi, welcome to the elasticity class. Today we are going to talk a little bit more about a different core kind of problems. Last few classes you saw this thing about the Prandtl stress function. Today we are going to see a different kind of problem. So let's get started. So in the previous classes we were applying forces to the ends. So here, that's not what we are going to look at. We are going to look at applying forces to the sides. Okay, turns out we cannot apply general forces to the sides, but we will figure out how to solve this, and this leads to two kinds of problems. One is called plane problem. The other one is called a plane stress problem. Notice the difference. One is called plane, the other one is called plane stress. We can do quite a lot on this. So we are going to look at a situation where the faces z equal to plus or minus h are free, so there is nothing here. All the forces are on the sides. Okay, so what are we trying to do here? So let's see if I can highlight this a little bit so you can see what is what. There, we are going to solve equilibrium. Okay, we are going to solve compatibility, but we are going to do that in a slightly different way. But nevertheless, we are going to solve the equilibrium problem. We are going to solve the boundary conditions. So notice it looks kind of complicated, and by the way, there are lots of calculations here. I'm going to only talk to you about the highlights. The notes will be available so you can actually look at the calculations, but I want to talk to you about the idea. Okay, and then so what is happening is on the lateral sides we are going to specify the tractions. Okay, this is the original problem. As usual, we cannot really solve this, so we say okay, fine, what can we do? Okay, the answer is we can solve what is called the plane problem. Plane problem, the idea is I am assuming that the tractions on the sides are only in the x and y direction. There is no z traction. Okay, that does not mean there is no z stress, there is just no z traction. Okay, so that's the idea. So please remember that condition. Okay, we will talk to you about that a little bit more in detail as we get along. Okay, so just to get you an idea of what I'm talking about. So what it is that I have the same prismatic body and I have tractions which are only parallel to the face, like that. You see what I mean? Nothing this way. That's what we mean. Okay, very good. Now, so what are we going to do? There is no z traction, no? So we will just assume as a starting point that there is only z displacement. So let's kind of blow it up a little bit so you can see it better. There's only z displacement, which means the strain is going to look like this, uxx, uxy. So there is no z strain, there is no there's no axial strain in the z direction, there's no shear strain in the z direction, everything is xy. This is called the plane problem. Displacements are only in the x and y direction. There is no displacement in the z direction. Remember earlier we talked about antiplane. Now this is called plane. Okay. So when you do that, the stresses look like sigma alpha beta is lambda. So now alpha beta and gamma go 1 and 2. So we are going to say when we wrote ijk, it's going to be 1, 2, 3. Now it is just 1 and 2. Okay. The interesting thing is, just because the displacements are plane doesn't mean that the stresses are plane. You know, this has to do with Poisson's ratio. You know what I mean? If I want to prevent things from making thinner or fatter in the z direction, I have to apply stress. There's no other way. So that's why I have sigma 3, 3. Okay. Now, what happens is, interestingly enough, your equations of equilibrium become just two equations. This and this. Okay. So just two equations of equilibrium. So by the way, what this means is that as usual, if you invert it, you will get epsilon alpha beta is 1 plus nu 1 plus nu over E sigma alpha beta minus nu times sigma gamma gamma delta alpha beta. You know, everything lives in the plane except that sigma 3, 3 is not equal to 0. That's the main deal. Okay. So what happens is, if sigma 3, 3 is not equal to 0, there is no way you can satisfy the top and bottom boundary condition. You're with me? So that's not possible because sigma 33 will not be 0. If sigma 33 is not going to be 0, the top and bottom are not going to be traction free. What are you going to do? So what you do is you add solutions for these two. We just solved this. This is Saint Venant problem. That is, you take this and use the Saint Venant problem to get rid of the tractions on the top and bottom. So you have to take the plane problem solution and add the Saint Venant problem solution in order to get rid of things, or subtract the Saint Venant problem solution. Depends. Okay. Typically, you will have bending moment, torsion, something like that on the cross section. You'll have to take care of it. Okay. The interesting problem is, you can, with this kind of an assumption, you can solve the equations of equilibrium and the displacement and the compatibility equations. Since we are guessing displacements, there is no question of compatibility. So equations of equilibrium exactly, lateral boundary conditions exactly, but as usual, top and bottom we will not be able to solve. Okay. So the other kind of problem is to assume that the stresses are only plane. Remember the previous cases, the strains were only in the x and y direction. Now you can also assume the opposite possibility is to assume that the stresses are only in the x and y direction. Now you will have bigger problems if you do this. There, if you assume that the strain was only in the x and y direction, the only problem was the fact that the boundary conditions could not be met. Now you have stresses in the x and y direction. It will turn out that you cannot meet the compatibility conditions. One of the compatibility conditions is the one that I have listed here. I'll blow it up a little bit and you can see. This compatibility condition epsilon yy comma zz minus 2 epsilon yz comma yz plus epsilon zz comma yy cannot be met. The only way you can meet it is if sigma xx plus sigma yy is a plus by. It turns out too restrictive, you cannot do anything. Okay, so if you start this way, you're screwed. Nothing will work. So what are you going to do? Well, we are engineers, no? We come up with a very clever idea. We say, okay, fine, it doesn't really work properly, but if I made a thin slab. So remember, this is still a prismatic body, but this is very small. Then what I do is, I integrate across the thickness. So I am doing what is called a membrane problem. Okay, membrane problem is where you apply forces to the ends of the membrane like a balloon, but nothing on the top and bottom surface. If you apply things to the top and bottom surface of the membrane like this, it will be called a plate problem. And then, so you have to take a separate class for that to figure out how to solve plate problems. So plate problems are this two-dimensional geometry where things are very thin, flat slab. Okay, so if you have a membrane problem, what you do is you look at not the actual displacement but averaged displacement. That's the whole idea. You look at the average displacement. If you look at the average displacement, again I will blow this up and you can see this better. If you look at the averaged displacement, you will find that sigma bar, which is the average stress, will only be a function of x and y. Sigma, all these things are averaged, and sorry about that, something got messed up. But epsilon bar is 1 plus mu over e, sigma bar minus mu over e, sigma bar, except that the Poisson's ratio and the Young's modulus will not be exactly the same as the original one. These are the correction factors. So your Poisson's ratio is not the actual one, but slightly different. Okay, so that's what will happen. So let me write this down. Poisson's ratio is nu over 1 plus nu, and then Young's modulus is E times 1 minus nu squared. So what happens is, for the plane stress problem, you have to use this as the Poisson's ratio and this as the Young's modulus. For a plane strain problem, you can keep exactly the original Poisson's ratio and the Young's modulus. For plane stress, you have to replace the Poisson's ratio and Young's modulus. Okay, so now what are we going to do? Okay, we now have a nice problem. What is the problem? We have to solve sigma xx plus or sigma bar comma x plus sigma xy comma y equal to 0, sigma xy comma x plus sigma yy comma y equal to 0, and then compatibility. Okay, that's what we're going to solve. How are we going to do this? Turns out to be beautiful idea. Whenever you have just two variables like this, we are going to use our curl theorem twice. Once for this, one for this, and actually not even twice, 3 times. Isn't that amazing? We're going to keep using the curl theorem over and over again. So let's see how that works. And this is the heart of what is called the Airy stress function. So what you do is, if you look at this guy, you will see I can use the curl theorem. That means there is a scalar function phi of xy such that sigma xx equal to phi comma y, sigma xy equal to minus phi comma x. This should look like your Prandtl stress function, right? The interesting thing is, not only for that, for the second one there is another Prandtl stress function. Sorry about that, let me get it back. So, sorry, let me get it right. Yeah, there you go. So, there's a Prandtl stress function here. There's another Prandtl stress function here. But the interesting thing is, because sigma xy is the same on both sides, the two Prandtl stress functions will be related by another curl theorem. And so, you will get a function which is called the Airy stress function. Airy stress function is the combination of two Prandtl stress functions. So that's why we do torsion first and then plane strain, because we want to introduce this idea of a Prandtl stress function there. So what happens is, now this Airy stress function has, now the Prandtl stress function 1 is a comma y, Prandtl stress function 2 is minus a comma x, and then it turns out sigma xx is d squared a dy squared, sigma yy is d squared a dx squared, sigma xy is minus d squared a dxy, sigma zz is nu times del squared a. So notice that not only do we have sigma xx, sigma xy, sigma yy, but also sigma zz. This will give us problems for boundaries, but we know how to fix it. Okay, so our idea is equations of equilibrium are satisfied by any a of x comma y if sigma xx is minus a comma yy, sorry, plus a comma yy, sigma yy is a comma xx, sigma xy is minus a comma xy. If you do that, it will satisfy the equations of equilibrium. And sigma zz will be nu times del squared a, we don't care, it will automatically satisfy. The problem is compatibility. Just like with Prandtl stress function. So in this case, it's actually easier, luckily for us, because if you actually look at the compatibility equation, it will turn out to be, rather than getting del squared psi, you will get del squared of del squared a equal to 0. This is called a biharmonic equation, this thing. This is called a biharmonic equation. Oops. So this is called a biharmonic. So the interesting thing is, just like the Airy stress, the Prandtl stress function, the functions phi and psi represent contour lines for sigma xx, sigma xy, sigma yy, just like the previous case, and the gradient of this psi will again tell you the max, the sigma xx plus sigma xy squared and all this stuff, just like with Prandtl stress function. It will also show up here. But the real deal is this A. If I know A, which is the Airy stress function, you can find phi and psi. All those things you can find. So the question comes about now, becomes a mathematics problem. How do you solve del squared A equal to 0? Sorry, del squared of del squared A equal to 0. That's where we are going to be.